Okay, so let's get started with today's lecture. Today is day 3 of the small language model workshop. And today what we are going to do is that we are going to do 3 things. First, we are going to set up the small language model training pipeline. We are going to see how to construct the loss function for the SLM. Then we are going to pre-train the small language model. And this all of us are going to do on our Google Colab notebook. And finally, we will also run inference. So the problem which we started with, if you remember, was taking the tiny stories data set and trying to construct a model which has only 50 million to 70 million parameters, let's say. And the whole goal was, can we do pre-training and can we construct a model which understands English language itself? So which understands the form and meaning of the English language. The challenge for us is that can we do it in less than 100 million parameters? So to work with this challenge, one of the key things which we saw in small language models is that we have to build a very specific data set. And the data set which we have been looking at is the tiny stories data set, which consists of stories, 2 million stories, specifically meant for 3 to 4-year-old kids. I'll do a recap of whatever we have seen so far. But first, what I want all of you to do is that this Google Colab code file, I'm going to share with all of you on the chat. And then we are just going to run the different code cells. The reason we are doing it at the start of this lecture is because till the end, when we reach the end, this should entirely run. So while this keeps running, I'll explain the theory to you, and then we can come back and we can check our results. So I'm sharing the code file on the chat right now. You can open it. And once you have opened it, there are a couple of things which I want to mention. The first thing is, as I've mentioned in the initial lectures also, how many of you have access to A100 GPU? Can you mention it in the chat if you do have access to this A100 GPU? So if you are on Google Colab Pro right now. Okay, it's great that you are on Google Colab Pro, because if you are on this, you will see the results of the small language model live in today's class itself. If you are not on Google Colab Pro, then you will not have access to A100 GPU. But still, what you can do is that you can use T4 GPU, which would be free for you. But this takes around 8 to 10 hours to run, I think. I've tried it on T4 and it's not very fast. Sometimes the laptop also crashes. So I do not recommend pre-training on this configuration. So what we are going to do is that, as I mentioned, we are just going to run the different code cells. So we are going to run until step number 8 here. And then I'm going to cover in today's lecture, I'm going to cover step number 5, step number 6, step number 7, and step number 8. So I'm going to mention all of these steps to you in detail. But for now, let's just run the code cells because it takes some time. So if we just do it later, we might not finish the running before the class ends. So to be efficient, what we can then do is run this code cell, step number 1, run this code cell. Then here we are loading the data set. Here we are tokenizing the data set. We have already seen this before. Here we are creating input-output data pairs in step number 3. In step number 4, we are defining the small language model architecture. This we saw in the last class. And today we are going to start seeing step number 5, which you can also run. Step number 6, you can run. Step number 7, and you can run step number 8 as well. And if you have run all of these 8 steps, that's good. This will keep running parallelly. Meanwhile, we'll go to the Miro board to understand the theory. So first, can I get a confirmation from people if you have run until these steps? It will take time. So it will take around 35 minutes or even more, I think. But for now, just run 8 steps, which I've mentioned on the Google Colab notebook, which I shared in the chat. So people who are coming in late, what we are doing right now is that we are just running the Google Colab notebook, which I shared until step number 8. I'm going to explain all the steps in today's class, starting especially from step number 5. But the reason we are running this at the start of the lecture is because while it runs, we can simultaneously understand the theory. So when this theory finishes, we can come back here and then we can understand the code again. Okay. You can run locally in Jupyter notebooks as well, but it might still take time. Instead, it's better to just purchase Google Colab Pro. That would be my recommendation. All right. So as this is running, just keep this running. So how many of you have started running this? Can you mention yes in the chat if you have run until step number 8? Only then I will go to the Miro board and I will start explaining today's content. We don't want the run to finish right now. It will take time. So let it keep on running. As we have seen before, the steps which take the longest time are the tokenization step over here. This takes quite some time. This itself takes around 15 minutes. Creating input output pairs takes some time. And then a lot of time will be taken in the pre-training stage. You can run on the M2 chip as well, but it's still having A100 GPU will be faster, I believe. You will need GPU to run this actually, whether it's RTX, whether it's A100, whether it's H100. T4 GPU, it's very slow, although it's available for free. Even if you don't subscribe to Google Colab Pro, everyone has T4 GPU. So even if you don't have Google Colab Pro, at least right now you should run it on T4 GPU, no matter which GPU you are on. So if you are on free plan, run it on T4 GPU. If you are on paid plan, run it on A100 GPU. All right, good. Now let's go to the Miro board and start today's content. As I mentioned, today we have to understand three things. How to set up the training pipeline. This includes the loss function. Then we have to understand how to do the pre-training itself, and then we have to run inference. Okay. Let us have a quick recap of what all we have seen so far in terms of the other steps. So in the last lecture, our main goal was something like this. If we take one, so if this is our input batch currently, and all of you should now be familiar when I say this is our input batch. What do I mean when I say this is our input batch? I mean the following. Each row here consists of an input sequence, and corresponding to every row, we have an output sequence which is shifted to the right hand side by one, right? And each batch consists of 4 input sequences in this case, because batch size is equal to 4. In last class, what we actually saw is if you take one input sequence, let's say 1, 11, 15, and 24, which corresponds to one day a little, we pass it through something which was a black box until the last class. And then the prediction of this something is the next 4 tokens. Uh, so if one is the input, the next token can be something random. If one day is the input, the next token can be, let's say, star. If one day O is the input, next token is boy. Or if one day a little is the input, next token is chair. These are the predictions of our LLM. And we know the ground truth, right? For one day is the output, for one day O is the output, for one day a little is the output, and for one day a little girl is the output. This is the ground truth. In the last class, we have only seen how to get till the prediction step. And to see that, we really uncovered the brain of the small language model. And what is the brain? It's this entire architecture which we saw. If you remember, we saw that this brain, or this question mark which I marked over here, essentially are 3 blocks which are stacked together. The first is the input block, the second is the processor block, and the third is the output block. Essentially, the sequence of tokens which we have, these 4 sequence of tokens, first go through the input block, they go through the processor block, they go through the output block, and finally what comes out of this output block are these 4 next tokens, right? Once we have the 4 next tokens, we will create the loss function, and then we will do back propagation, which we are going to see in today's class. But again, I want you all to recap the journey which we have seen. And the best way for us to recap this journey is to actually see what happens to a single token as it goes through this brain of the small language model? What happens to a single token as it goes through all of these steps? So what happens is that first, let's say if you have this sequence, right? This is the input sequence, let's say. And if you look at friend, this word is initially isolated from its neighbors. Then it's assigned a token ID. We have a vocabulary and a token ID is assigned. So these numbers which I was showing you over here, these are the token IDs. The real magic begins after this step, right? Once you assign the token IDs, then what you do is, so think of the token ID as a badge or a roll number which a student has in a class. Then that student is given a set of questions, let's say 768 questions. That's the embedding dimension. And essentially every token ID is converted into a higher dimensional vector, which is called as the token embedding vector. In this case, the embedding size is equal to 768. This embedding dimension can be chosen, and in GPT-2, it was chosen to be 768, but it can really be anything. So the first step is converting token ID into token embedding, and position is also important along with the semantic meaning of the token. So let's say friend appears in position number 3. We convert this position itself into a 768 dimensional embedding. That's the positional embedding. So eventually our hope is that the token embedding will retain the semantic meaning of that word when all these parameters, all these 768 parameters are trained. And our hope is that positions will also be captured, because as we have seen in the last class, the position where a particular token appears also changes the context. And there is a question in the chat regarding, are these embeddings used as parameters? If you recall in the previous lecture, we have a token embedding matrix and a position embedding matrix. These values are not known beforehand and they are parameters. The token embedding is then added to the position embedding, which gives rise to an input embedding. You can think of this as the uniform which the student has before they get on a train to the transformer block. Now, the transformer block train consists of multiple compartments. In fact, it consists of 6 compartments: the normalization block, the multi-head attention layer, the dropout, shortcut connections, another normalization layer, feed forward neural network, and another dropout layer, followed by a skip connection. We saw this in the last class in a lot of detail. Can someone tell me which is that component in this architecture where we capture the context? So when, let's say friend, right, it has a uniform, and when it onboards onto the transformer block, it really has no clue what are the tokens surrounding it. There is one place in the transformer block train where this context is captured. Yeah. And that's essentially the multi-head attention block. The multi-head attention block is the only place in the transformer block where a token learns about its neighboring tokens, where a token learns how much importance should be given to the neighboring tokens. So this uniform, it's called as an input embedding till it goes into the attention block. But once it comes out of the attention block, it's called as the context embedding or the context vector, because now it contains a much more richer representation of all the other tokens surrounding that particular token. After that, another major block is this feed forward neural network, where we have expansion into a higher dimensional space and the contraction, so that we learn about richer representations. If this feed forward neural network is not there, it turns out that the LLM cannot really understand the context and the meaning of the questions which is asked to it. Now, this itself, if it's looking complex to you, remember that there are 12 such transformer blocks or multiple such transformer blocks. The GPT-2 smallest model had 12 such transformer blocks. So you have one transformer block here, one transformer block here, one transformer block here, etc. And these are in sequence. So once we get out of the first transformer block, we go to the second, then we go to the third, then we go to the fourth, fifth, etc. And when we come out of these multiple transformer blocks, that's when the processor part is truly over. And then we go to the output block. In the output block, what happens is that every token now has 768 dimensions, right? Till it reaches the output block. But in the output block, we have this layer called the logits layer, where this 768 dimensional vector is kind of transformed into a vector of the vocabulary size. So if the input is a true, friend accepts you, when it goes to the output, it's converted into a vector of the vocabulary size. And then what we do is that we just look at that ID, that token ID, which has the maximum probability, and that's going to be our predicted next token. So it can be something completely random here, maybe boy. For true, we look at that token ID which has the maximum probability. So let's say if it's token ID 500, we go to our vocabulary, we decode what token corresponds to 500, and that will be the prediction over here. Let's say university. Similarly, we make the prediction for friend, accepts, and you. So these are my predictions right now. Initially, when the SLM starts training, these predictions are random. Eventually, our goal is to make sure that these prediction values match the actual values pretty well. The prediction values should match the actual values. And that is how we define the loss function. So this is the place where we start today's lecture. Does anyone have any questions in this so far? Until now, whatever we have seen? Because the last lecture was very comprehensive and I had told you to again go through the last lecture in detail. Would the embedding vector for position numbers always be constant? So please keep in mind that these numbers or these parameters are not actually constant because we train them, right? The position embedding vector for each token and the token embedding vector for each token are trained with time. So it's not really constant. Can you please explain why position embedding layer is block size into the embedding dimension? So block size in this case is equal to the context size. And if you remember, the input output pairs really look something like this. The input output pairs look something like this, right? So the number of positions which actually can take place is restricted by the context size. We won't have positions which are greater than the context size. That's why the size of the position embedding matrix is determined by the context size. Is context window less in SLM than LLM? No, not really. So context window does affect the number of parameters for sure, but I would not say that for all SLMs it's really less. So WTE, which Mohit you are mentioning in the chat, that is the token embedding matrix. There is a difference between WTE and WPE. PE is the position embedding matrix and TE is the token embedding matrix, right? So that's different. If you see in the last class, we have seen token embedding matrix has dimensions of embedding dimension, which is 768. And the number of rows are equal to the vocabulary size for token embedding matrix. However, for position embedding matrix, the number of rows are equal to the context size. That's the difference between these two matrices. We have already covered this in the previous lecture. Okay, now let me go to the next portion of today's lecture, which is essentially first starting out with understanding how do we calculate the loss function. So can someone try to think, let's say if you have the actual tokens as these, okay, and if you have the predicted tokens as these, how can you compute the loss? Just try to think from first principles over here. Even if you don't know the answer, it's fine. But if you have learned about this in traditional machine learning, for example, you know what the predicted tokens are and you know what the actual answer needs to be. Target minus predicted. Many people are saying predicted minus target, doing the subtraction. But subtracting what essentially? Because nothing is trained right now, right? Nothing is, you don't know the actual embedding for these because we are training the embeddings also from scratch. Okay, so it's actually pretty simple. Let me explain to you how this is done. Let's say we had these set of input sequences. I had always thought, okay, and this input sequence goes into the GPT model, and then we have predicted tokens, right? So let's say we have this logits matrix like this. I had always thought, and then each row has the vocabulary size. And remember what we discussed, we have to take a look at that ID which has the maximum probability, right? So let's say it's these IDs, and the decoded tokens are something random like this, since we are using a subword based vocabulary. Remember that we also know our target token IDs. So the target is, if I had always thought is the input sequence, the target is shifted to the right hand side by one. So the target is had always thought and Jack. And that corresponds to the token IDs, let's say 23, 3881, 11223, and 15. So we know what the correct token IDs are. Now, can you think about the fact that, remember that if I look at I know that token ID number 23 needs to have the maximum probability. Ideally, if my model is good, token ID number 23 needs to have the maximum probability. So how now can you think, how can I construct the loss function? Think of the fact that I know the actual ID in each row which I want to have the maximum probability. What do I mean by this? So essentially, if you look at row number one, if you look at row number one over here, I want token ID number 23 to have the maximum probability. If I look at row number two, I want token ID number 3881 to have the maximum probability. If I look at row number three, I want token ID of, let's say, 11223 to have the maximum probability. And if I look at row number four, I want token ID number 15 to have the maximum probability. So now can you think what needs to be done? Now how can I find the loss function? Difference between the probabilities of the token predicted and the actual token. So that's actually not the correct answer. So if you have studied about the cross entropy loss, softmax of probability. So softmax is already applied over here, right? When we apply softmax, we get each row will sum up to one. So softmax is already applied over here. So the way we do it is that if, let's say, in row number one, right, you want the token ID number 23 to have the maximum probability. So ideally, what would you want this probability to be? Ideally, what would you want the probability to be? One, right? You would want the probability to be one. So what you simply do is that you check what the probability is for ID number 23. So, so you create a vector of actual probabilities. And let's say for ID number 23 in row 1, it's very low, it's 0.1, which is quite bad. For row number 2, you check what the actual probability is for ID number 3881. So let's say that is 0.3. In row number 3, you check the probability for ID number 11223. That's 0.4. And in row number 4, you check the probability, it's 0.1. And actually, you want these probabilities to be 1. Now, how do you construct the loss function? Because this is exactly, we cannot subtract it from 1. Because you can actually do that, but there is a better way of finding this loss function, which is usually done in logistic regression or traditional machine learning. Cross entropy, right? What if you simply take a logarithm of this? What if you simply take a logarithm of this? Or put simply, what if you take the negative logarithm of this? So now, until now, let's say we have probability 1, probability 2, probability 3, and probability 4. The loss function is constructed like this. It's negative log P1 plus log P2 plus log P3 plus log P4. Let's check whether this makes sense or not. If P1, P2, P3 and P4 are all equal to 1, this will become 0, right? Which means our loss is indeed becoming 0 when all these probabilities are equal to 1, which is what we wanted. But if the probability is between 0 to 1, if you see if the probability is 1, then the negative loss becomes 0. We are over here. But as the probability diverges from 1, so as we go here, as it diverges from 1, the loss actually increases. This is exactly what we want. The more these probabilities diverge away from 1, the more we want the loss to increase. This kind of a loss function which we are defining here is called as the negative log likelihood. And this is very, very commonly used in several machine learning classification tasks, logistic regression, etc. Does everyone understand this loss function? How we constructed this loss function? And why are we taking log really? The reason we are taking log is because we want the loss to be 0 at probability equal to 1. And we want the loss to actually increase as the probability goes further away from 1. So once you have these probabilities P1, P2, P3, P4, you want them to be as close to 1 as possible, right? You want this. How do you enforce that? As some of you are saying, maybe we can do something like this 1 minus P1 square plus 1 minus P2 square plus 1 minus P3 square plus 1 minus P4 square. This also can be done, but the much more easier or sophisticated way of doing this is by taking log, because when you are in the probability space, the notion of distances really don't make sense. You cannot, when you subtract two probabilities and take the square, it mathematically does not make any sense. It's fine to do this in the case of regression because those are actual values. But when you're dealing with probabilities, converting a loss function into logarithm is much more better. It's easy to understand, and differentiating this is also quite straightforward. So with this same loss function, now we are going to find the loss. So this thing which we started today's lecture with is, let's say we have some ground truth, right? We have some ground truth and we have prediction. The loss which is actually found is this formula, log of P1 plus log of P2 plus log of P3 plus log of P4. And what are these P1, P2, P3 and P4? P1, P2, P3 and P4 are the probabilities which we want to be 1. The probabilities associated with token IDs corresponding to our ground truth, which will not be 1 initially. Initially, we'll have a pretty high loss because initially the output tokens which are generated, which will be completely random. So is this clear? Does anyone have any doubts or questions in this part so far? You can feel free to ask it in the chat. Sum of P1 plus P2 plus P3 plus P4. So the thing which is main thing which we want to understand is we want P1 to be close to 1, we want P2 to be close to 1, we want P3 to be close to 1, and we want P4 to be close to 1. We want all these probabilities to be as close to 1 as possible, right? So ideally what we want is we want this P1 multiplied by P2 multiplied by P3 multiplied by P4, because we want P1 to be close to 1, P2 to be close to 1, P3 and P4 all to be close to 1. So there is and P1 and P2 and P3 and P4. But log function has the property that log P1 plus log P2 plus log P3 plus log P4 is the same as this. So it works out that way. So the desired token prediction related expression is selected as negative log. Yeah, exactly. This is the main point to consider. All the other tokens are completely ignored. So if I look at I, the number of columns here are 50257, right? Which is equal to vocabulary size. We are only interested in that token ID, which is in our target. We are only interested in the fact that that token ID becomes as close to 1 as possible. Why? Because we are doing softmax. So all these probabilities have to sum up to 1. So if this becomes close to 1, we are ensuring kind of that all other probabilities go to 0 as much as possible. So it works out even if we try to maximize one probability, since all of them are anyways going to sum up to 1, all the others will automatically take care of themselves. What about others? Are there any questions here in the loss function? This is very important to understand. Won't we get the same output each time? So the ground truth is the same, that is correct, but you won't get the same output each time, because why? To get to this stage, can all of you try to think why won't we get the same output each time? The reason we won't get the same output is because till the time we reach the logits matrix, right? Till the time we start from the input, then we go to the transformer and we go to the logits. There are so many trainable parameters here. We have gone through around 100 to 150 million trainable parameters. All of these are knobs which can be tuned. The moment a knob is tuned, our prediction changes. Yeah, it's kind of like improving with time. Now let's come to the next section, which all of you or many of you might already be thinking that. Remember, currently we are only looking at one input sequence, right? But what if I get a batch? So let me clarify this further. So let's say you have an entire batch like this. Until now, let's recap what all we have seen so far. Until now, what we have seen so far is, let's say we take these 4 tokens. Um, yeah, let's say we take these 4 tokens, right? We take these 4 tokens. What we have seen is that we get a prediction. We get a prediction token IDs of some random 22, 233, 11 and 2, let's say. And we know that the actual values need to be these 4. So then we constructed a loss function between these. Correct? That's what we have seen so far. And this gives us the loss, let's say L1. But how do you find the loss for an entire batch? Remember, the way this is going to work is that we are going to take one entire batch. We are going to find the loss for the full batch, and then we are going to do back propagation. So it is not just enough to understand how loss is found for one input sequence. Uh, what is important is how do you find the loss for each of these? So the way it works is actually quite simple. You have obtained L1, right? Then you will obtain L2, then you will obtain L3, and then you will obtain L4. So the way you find the loss for an entire batch is you take the average across all the samples of the batch, L1 plus L2 plus L3 plus L4 divided by 4. That's the loss on one batch. So when we go through the forward pass for one batch, we find the loss. Until now, even if you understand this much is enough, we'll see how to do back propagation later. So the way the loss is calculated for a batch is actually something like this. Uh, Currently, we have got these targets, right, for one batch. For multiple batches, let's say for one batch, let's say you had P1, P2, P3, P4, and if you find these losses, if you had 2 batches, your output probabilities would look like P1, P2, P3, P4 for the first batch, P5, P6, P7, and P8 for the second batch. So then the loss is just going to be minus 1 by 8 log P1 plus log P2 plus dot 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 log P8. This is how you find the loss for the entire batch. It's actually doing the same thing what we did for one batch, but for multiple batches. Uh, so we are kind of averaging it out. there is a question before softmax, the scores can be negative. So why do you call them probability? Actually, we are calling them probability only after softmax is applied. So the way it works is that you get the logits matrix, you apply softmax, and then you get this matrix of probabilities. This is that matrix which we are looking at, where every row sums up to one basically. Two input. Okay, did everyone understand this much? So until now, what we have seen so far is the fact that, okay, what we have seen until now is, let's say you get an input sequence. How does it go through the entire architecture to give you the next four tokens? How do we get the loss based on one input sequence? And then how do we get the loss for one batch? We get the loss for one batch. So can everyone mention to me if this entire forward pass is clear to you? What all we have figured out until now is called as the forward pass. So basically you start with so there is a question, can you recap on the loss function once? Yeah, sure. So let's go from the start so that you get a clearer view. We have an input sequence, right? Let's say one day a little, that goes through this entire architecture, the input block, the processor block, and the output block. Once it goes through this entire journey, and remember, we have seen this journey of a token through an LLM architecture. So if you're confused about this journey, just remember this whole journey which a token goes through. So finally, when we come out of this journey, we have the next four tokens, correct? So if ground truth is something and we have these predictions, right? The question is that how do you find the loss function if you have prediction values and you have true values? The way the loss function is found out is by looking at this output probability logits tensor. Once we come out of the architecture, we have this tensor which is called as the logits tensor. You can think of it as the tensor of probabilities, right? So if I look at the first token I, the way we get this out, the way we get the next token is that in this row, we look at that token ID which has the maximum probability, and then we find what the token corresponding to that token ID is. That's how we get these predictions. But for each token, we also know what the actual prediction should be. That's the ground truth. So let's say for I had always thought the ground truth is this input shifted to the right by one, which is had always thought Jack. And that corresponds to token ID number 23, 3881, 112223, 15, let's say. So ideally, if our model is perfect in an ideal world, we would want the probabilities associated with these token IDs to be equal to 1. For example, if I look in my first row, I would want the probability associated with token ID number 23 to be equal to 1. If I look at the second row, I would want the probability associated with token ID number 3881 to be equal to 1. But that will not be the case because we are not in an ideal world. We have just started training. Answers will be random. So what we do is we collect these probabilities. We collect the probabilities at location number 23, 3881, 11223, and 15. And we call them P1, P2, P3, and P4. Those will not be 1. We want them to be 1. We want these probabilities to be as close to 1 as possible, but they won't be. So the way we construct the loss function is by taking log of P1 plus log P2 plus log P3 plus log P4. If all these probabilities are equal to 1, you will see that this sums up to 0. So our loss becomes 0. But if these probabilities start diverging from 1, so for example, if these probabilities start diverging from 1, our loss increases. That's how the loss is found out. And this is the loss for one input sequence. The way we do it for an entire batch is that instead of P1, P2, P3, P4 for one batch, for one input sequence, if a batch has two input sequence, we kind of concatenate them together. And then the loss is found out by minus 1 by 8 log of P1 plus log of P2 plus dot 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 log of P8. That's how the loss function is found out. Okay, so if still something is unclear, I would really encourage all of you to go back through this lecture and Watch this part again, because whatever we have covered until now, that's essentially the forward pass. So what is the forward pass? Let me explain to you again. The forward pass is basically taking in a batch of inputs. The forward pass is taking in a batch of inputs, passing them through the SLM architecture, then getting the predicted next tokens, then finding the loss function with the ground truth. That's all. This whole thing which I've shown on the screen right now, this entire thing is called as the forward pass. Okay. And once you get, once you finish the forward pass, you get the loss, right? And now think about it this way. The loss is a function of millions of parameters. The loss is a function of, let's say, 1 million parameters. And what I want to now do is that I've got this loss and I want to adjust these parameters so that my loss decreases. And how do we do this traditionally? Now it's very simple. After this point, we just resort back to our usual gradient descent. Because let's say if you have a two-dimensional loss function, right? And you know that the loss is minimized over here, but you are not at that point yet, you are at some random point. How do you minimize the loss? You go in the direction of the steepest descent, and hopefully you hope that you might come to this local minima. This is exactly what we are going to do now, but for these 1 million parameters or 100 million parameters which we have. What we are going to do is that we are going to find the partial derivative of the loss with all of these parameters. With respect to P1, we are going to find the partial derivative of loss with respect to P2, and we are going to find the partial derivative of the loss with respect to, let's say, the 100 million parameter. And then every single one of these parameters we are going to update. So if you are aware of the way vanilla gradient descent works, it's something like this. The first parameter we update like this. The second parameter we update like this. Similarly, the 100 million parameter will be updated like this. This thing what we are doing here right now, it's called as the update rule. And I'm showing you a very vanilla gradient descent here, but the actual update rule is slightly a bit more complicated version of this, which is called as the ADAM. But at the heart of it, we are kind of doing the same thing. So what we essentially do is we process one batch, we find the loss, we find the gradient of the loss with all the parameters, and we update the parameters. That's it. That's one entire loop. Then we process another batch. So batch one comes in, loss is found out. Then you do the update rule. Then when you go back, we have a different batch, right? The same batch is not processed. So this is called as batched gradient descent. So you update the parameters after each batch is processed. So you do one batch, you update the parameters. Go back, do the other batch, do second batch, update the parameters. So as you process the different batches, you will hit one limit where the entire data set is covered, right? You, let's say, process one batch. So this is my entire data set, and my one batch is this. Okay, I process one batch, then I update my parameters. I process my second batch, then I update my parameters. There will come a time, let's say at maybe batch number 800, that I cover my entire data set. This, when we cover the entire data set, is called as one epoch. Essentially going through the entire data set once, it's called as one epoch. And when you do traditional machine learning, you would probably do 50,000 epochs, 60,000 epochs, etc. But for training language models, even if you do 2 epochs, 3 epochs through the entire data set, it's fine. The model learns because the batch size itself, uh, one run through the entire data set is usually enough. Okay, so this flow which I explained to you right now is exactly how the parameters of a language model are tuned. So many people had the question at the start, what are these parameters? Are you all now clear where these parameters came from? So in last class, we actually saw wherever there are tunable parameters, we mark them with P. So to give you a quick recap, where all there are tunable parameters, if we are a detective right now and trying to find out, okay, in this entire thing, where are the tunable parameters? So let me ask you this, what is the first place where there are tunable parameters in this architecture? What's that first place where tunable parameters come in? So if you are unable to answer this question, it means your understandings are not clear of the previous lecture. The first place where there are free parameters are token embeddings. Okay. And what is the size of what's the number of parameters which we have here? We have a token embedding matrix whose size is equal to vocabulary size multiplied by the embedding dimension. We have seen this in the last class in a lot of detail. It's not 4 into 768. That's the wrong answer. 768 part of the answer is correct, but why did you mention 4? It should be the vocabulary size, right? For one input sequence, it's correct, but the total number of parameters, it's actually 50257 multiplied by 768 because I need token embedding for all of my tokens, right? So it's vocabulary size into 768, right? All of you who are answering that are correct. Now let's come to the second place. What is the size of the positional embedding? What are the number of parameters here? No, it's not 768. That's not the correct answer. What about others? It's not 768 into 4. Yes, the correct answer is context size multiplied by embedding. The size of the position embedding matrix is the context size multiplied by the embedding dimension. Why? Because we need one embedding vector for each and every position. And how many positions are there in one input sequence? The number of the context size, right? So the answer is context size into the embedding vector. So if this is not clear to all of you, then again there is some. So if you are saying 4 into 50257, that is not a correct. It's a correct answer if context length is equal to 4. But if context length is equal to 768 or 1024, so it will not be 768 into 50257. That's also not correct. If the context window is 1024, the number of parameters in the position embedding matrix will be 1024 by 768. The number of parameters in the token embedding matrix will be 50257 multiplied with 768. Okay. Uh, why token embedding is vocabulary into embedding size? So basically the answer for this is again, you essentially need an embedding for all the tokens, right? All the token IDs. And how many token IDs do you have? Just check out the journey of a token. How is token ID assigned to a token? You go to a book of vocabulary. So this book of token IDs which is there, this is my book of token IDs, right? And how many token IDs do I have in this book? You can think of it as an encyclopedia or dictionary. It's my vocabulary size. That's why the size of the token embedding matrix is 50257 multiplied with 768. What's the next place where we have trainable parameters? We finished token embeddings, we finished position embeddings. What's the next place where we have to? So Mohit's question, so Mohit, your question is correct in terms of parameters, right? But when you add, the only thing which matters is the number of columns, which is still equal to embedding dimension. So when you look at one sequence, the token embeddings will be 4 into 768. Position embedding will also be 4 into 768. So when you add, it's the number of dimensions which are added, which are same for both, which is 768. So the next place where there are parameters is actually the multi-head attention, right? And the parameters present them in the form of trainable matrices WQ, WK, and WV. Here there are trainable parameters, and the dimensions are again the embedding dimension and the output also can be equal to the embedding dimension. Then what are the number of parameters in the feed forward neural network? We have seen this in the last class, but many of you made a mistake here. Can you again tell me what are the number of, if our embedding dimension is equal to E, what are the number of parameters in the feed forward neural network? 4 into E is the wrong answer. E into 4 into E is better, but it's still not correct. Yeah, so basically it is E into 4 into E multiplied by 2, because this is usually how that feed forward neural network looks like. The first layer has number of parameters equal to E, the second layer has 4E, and the last layer has equal to E. And since this is a dense neural network which is fully connected, everything will be connected to everything here. So the number of parameters here will be E into 4E, and the number of parameters in this compression layer will again be E into 4E. So the total number of parameters will be E into 4 into E multiplied by 2. Okay. So all of you who have given different answers, I hope this is now clear, because last time also everyone made a mistake here. But I can see Himanshu got the correct answer. Sita, Ruchiro was also almost already correct. But Lakshman and Mohit, vocabulary size does not come here at all. In fact, vocabulary size only comes at two places. Vocabulary size comes when we have the token embedding matrix and when we have this logits matrix over here. Now remember that currently we are discussing about one such transformer block, right? But eventually there will be 12 such transformer blocks or multiple transformer blocks. So the number of parameters will be multiplied by 12, whatever we are discussing right now. So these are the tunable parameters in the input layer. These are the tunable parameters in the transformer block. What about the tunable parameters in the final layer? Can someone tell me the formula for the number of parameters in the final layer? In terms of, let's say, embedding dimension and vocabulary size. You can try, even if it's wrong, it's fine. E into E is not correct. Vocabulary size into embedding is correct. Because if you see in the final layer, what is happening is that, take a recap of what happens in the final layer exactly. What happens in the final layer is that we have, let's say, 4 tokens in the input sequence with the embedding dimension 768, right? In the final layer, what happens is that they are converted into a 50257 dimensional vector. So we have a neural network here which is 768 into 50257, which is the embedding size multiplied with the vocabulary size. Those are the number of parameters in the output layer. So if you see, there are only two places in this whole parameter table where vocabulary size comes into the picture. That's the token embedding matrix. That's the token embedding matrix and the output layer. And that's why people say that we should not have vocabulary size of very large magnitude, because the number of parameters scales with the vocabulary size here and here also. All of these parameters which we just discussed in the input plus processor plus output, they add up together to constitute a language model. So here when we are discussing the back propagation rule, when we are discussing this back propagation, when we are discussing all these parameters, now you know which are these parameters we are talking about. Right? In the first lecture, many of you asked what are these parameters, where do they show up? The parameters show up at multiple places: token embedding matrix, position embedding matrix, trainable query matrix, trainable key matrix, and value matrix in the attention mechanism, feed forward neural network, 12 such transformer blocks, and finally in the logits matrix towards the end. These all parameters add up to around 100 million, right? And if you take a look at the way these parameters scale, the two variables which or three variables which affect the number of parameters the most are these variables called V, E, and C. The vocabulary size, if it increases, the number of parameters increase proportionally. The embedding dimensions, if it increases, number of parameters increase proportionally. The context size, if it increases, number of parameters increase proportionally. Okay. All of these parameters are updated using our update rule when we do back propagation. When the V size will be 50257, yeah, we process only one sequence at a time. That is correct. But when you are processing, let's say you are processing this batch, right? And when you need a token embedding vector for some token ID, how will you get it? When you need the token embedding vector for this token ID, how will you get it? The only way to get it is look at your token embedding matrix, which has 50257 rows, and look at row number 11, and then get the embedding vector from here. So you need to maintain this 50257 multiplied by 768. Those are where these trainable parameters come from. Okay, so this is how these parameters are updated after every batch. Remember, batch size is very crucial when training LLMs. If you don't have any batch, your LLM will never converge because you cannot wait for us to go through the entire data set before making the parameter update. You have to process it in batches. If V is less, will it not affect prediction? It will definitely affect prediction. So the vocabulary size at the start completely affects the prediction. And how do we know this? We know this because our hands have been burnt, right? Because if you saw GPT-2, let's take a look at the vocabulary of GPT-2. It had a vocabulary size of 50257, right? But it was really, it did very bad at Python code. So there is this blog which I had written about tokenization and LLMs. But the main purpose here is GPT-2 was very bad at dealing with Python code because its vocabulary size was actually not enough. So GPT-4o increased the vocabulary size and made the merging rules better. That's why its performance on Python coding improved. So if something is not working in your SLM pipeline, architecture might not be the only issue. The issue can also be how you have constructed your vocabulary itself in the first place. If the batch size increase, convergence would happen quicker. No, that is not guaranteed because if the batch size increase, to make every update, it takes more time, right? To make every update right now, I have to wait for one batch to proceed. So if batch size increases, my update time gets a bit longer. But then you might ask, why don't we have a lower batch size? Because that leads to noisy gradient updates. So there is a trade-off with lower batch size, and there's a trade-off with lower batch size. It's also not good. Higher batch size is also not good. So you kind of lie somewhere in the middle. So the pre-training loop of a small language model looks like this. Okay. For every iteration which we are going to do, we are going to choose a batch. The batch has input and target pairs. We are going to pass the input through the model to get the logits, which is the predictions. Then we are going to compute the loss. Then we are going to do back propagation. Then we are going to update the parameters. That's it. This is the entire training loop which our small language model is going to go through. There are two more things which we are going to see in the code. The first thing which we are going to see is the learning rate. So the optimizer which I showed you was a simple gradient descent, right? But typically, when we do optimizations using language model, there is an advanced version of the optimizer called ADAM or ADAM W. Now, in this advanced version, the learning rate is not fixed. The learning rate goes on changing with time. So we are going to have a learning rate something like this. We are going to ramp up the learning rate initially so that we can quickly discover patterns in the underlying data. And then we are going to ramp down the learning rate. Um, so it will kind of, why don't we have a fixed learning rate? Because the progress can be then very slow. So a fixed learning rate can be too small. And if the learning rate is too large, that's also not very good for us, because then the training will actually be haphazard or oscillatory. So we start with a kind of, so it's exploration versus exploitation, right? We start in an exploratory phase where we have a large learning rate to explore. And once we settle into places of local minima or good loss landscapes, then we have an exploitation phase where we kind of decrease the learning rate a bit so that we can have a stable training. This is one thing which you will see in the code. The learning rate follows this pattern. The second thing you will see in the code is something called gradient accumulation steps. So sometimes what happens is that if my batch size is too large, let's say if it's 1024, this 1024 cannot fit in my GPU. So if my GPU memory can fit only 32, let's say, if my GPU memory can only fit a batch size of 32, then how do you work with a batch size of 1024? The way you do it is that you first process 32 input output samples. You find the first gradient G1, then you process the next 32, etc. So you process G1, you process G2, then you process the 32th sample, and then you divide by 32. So essentially you divide the batch size of 1024 into smaller chunks of 32 each, so that it can process, so that it can fit in the memory. And this advice you can keep in mind when you're training your own SLMs. Sometimes you will get out of memory error. You will get that out of GPU memory. This problem can be solved with gradient accumulation, where you only save for a certain amount of time steps in the memory. You then do the gradient for the next 32, then the next 32, and then you take an average. So at any point, only 32 input output pairs are saved in the memory, not 1024. One more reason you need to have batches is otherwise you cannot store the entire, all the gradients in the memory. What is convergence? So it's not like, uh, what is convergence, right? How do we know? So it depends on the validation set which we have. Usually that point where the training and the validation loss are both decreasing simultaneously, it means it's good. Uh, and if the validation loss starts to increase, then we are overfitting. Then we should stop at that number of iterations. So there is a difference between parameters and hyperparameters. How many of you know this difference? How many of you know the difference between parameters and hyperparameters? Parameters are something which are trained during the training process, right? Like all the 100 million parameters which we saw. Hyperparameters is what an ML engineer or an LLM engineer has to fix before the training starts. While training an SLM, there are multiple hyperparameters. The first is the embedding dimension. The second is the context size. The third is, of course, the vocabulary size. The fourth is the number of transformer blocks. The fifth is the number of attention heads. And another one, actually, if you might consider it, is in the feed forward neural network, we have this embedding going into four into embedding and then coming back to the embedding, right? This four also is a hyperparameter because there is no logical reason for why we only go with four. It can be 2 or 6, etc. So you'll see in the code, when we pre-train the code, there are all of these parameters which are actually fixed. Actually, that's a good moment. Yeah, and there are hyperparameters with respect to our optimizer itself. So there are hyperparameters with respect to the architecture which we have seen over here. And then there are hyperparameters with respect to our optimizer, right? Like learning rate is a hyperparameter. Then the learning rate decay schedule is a hyperparameter, etc. This is a good point to take a look at our code and what is happening right now. How many of you actually ran this step number 8 and finished 20,000 epochs like I have over here on the screen? What's the loss function which you are seeing? Can you mention on the chat? What's the final loss function which or final loss value which you are seeing? You can just copy this and paste it on the chat. Okay, so this loss value is very similar to my loss value. Okay, very good. Almost everyone who has reached here has got great values of training losses and validation losses. Shravan, your values are not looking very good actually. Oh, because you are only at epoch 500, right? Are you using T4 GPU? At epoch 500, it's fine to have those losses. But everyone else, Dishant, Priyanka, Sita, Fazil, Monideepa, Avoga, all of you have great losses. Guru Prasad, okay, you are still at epoch 6500, right? Okay. Alok, you are getting an error. I think you did not run one code block. You might have not run one code block above. So those of you who have reached till this point, what you can do is you can plot your loss function here, and you should see something which I am seeing right now. Uh, there is a question, what did you mean when you said 2 to 3 epochs are fine? That's a good question. So basically, here what we are meaning epochs is actually, it should not be called epochs. What we are really doing here is that we are printing after we go through 500 batches. After we finish 500 batches, that's when we are printing. So it should be called as something different here, but epoch is usually when we cover the whole data set. Yeah, like a grouping of batches. Can someone share the code link? I will share the code link in the chat. So almost everyone who has reached the end now, you should be able to see this loss function. And the final test for us is going to be inference, where what are the output generated by our model. We'll come to this later. But first, let us see what is going on in this code. First, take a look at this configuration. You remember I mentioned about the hyperparameters. This block size is the context size. N layer are the number of transformer blocks. N head are the number of attention heads. N embed is the embedding dimension. This dropout is, you remember when we actually saw the architecture that there are dropout layers. So dropout, actually the dropout rate governs how many of those neurons, if you think as light bulbs, how many of what fraction of the light bulbs you want to turn off. That's the dropout rate essentially. Okay. This 6 here is the number of attention heads since it's multi-head attention. Usually people don't call blocks as blocks, they call them as layers. You will see them in all the code. But this is actually the number of transformer blocks which are attached together. So in this Miro board, what we have seen as the train compartments being attached together, right? Like here we saw these multiple blocks, those are called as layers. And here we have 6 layers. Okay. Vocabulary size is 50257. So these are the configurations which we use and the loss function. Okay. So now when I say the loss function, all of you should know exactly what I mean over here. When you estimate the loss is for one batch. So what you do is that now all of you should be able to link back the input output pair creation which we saw. The way it works is that you first call this function called get batch. And if you remember what the get batch function actually does, we saw this in the first lecture itself. What the get batch function does is that it randomly selects the get batch selects, let's say, if the batch size is 4, this is my first input output pair. This is my first input output pair. Then I select my second input output pair. Then I select my third and then I select my fourth. That's what the get batch function does. Essentially, what the get batch function does is that these matrices which we have assembled, it assembles that. Get batch assembles one full input tensor and one full output tensor. That's what's done over here. So x comma y equal to get batch. Now all of you should really understand what this means. What does this mean? X comma y is this get batch. So x is equal to this and y is equal to this. And we are going to find the loss for this one batch through L1 plus L2 plus L3 plus L4 divided by 4, right? That is how we are going to do it over here. And so here you see, we take the mean. Mean is because we process one batch, second, third, fourth, and then take the mean. So this is the estimate loss function. I hope all of you now understand what exactly is going on in this function. And the question is that where do we implement the loss, right? So there is, let me show you where loss is implemented, right? If you go to our SLM model architecture, step number 4, in the last class, we saw normalization block, self-attention block, and we saw this forward pass, right? What did we see in the forward pass? We essentially saw that first you take the token embedding, you take the position embedding, you add the token embedding plus the position embedding. So until this point, that's the uniform which I mentioned over here, right? This uniform, it's the input embedding, token plus position embedding. Then you go through the journey through the transformer blocks. And there are 12 such transformer blocks, or how many ever we have defined. Whenever you come out of the transformer block, this LNF is the output head, which is the neural network which maps from embedding dimension to the vocabulary dimension. And this is the loss function which we just saw. The cross entropy loss is this. So whenever you run a forward pass of the GPT model, you actually get the logits and you get loss. You get two things. This is the loss which is being accessed over here. You get these X and Y, you pass them through the model, you go through the forward pass, you get the logits matrix and you also get the loss. And then you'll also see that here I've written a generate function. We'll come to that later. Don't worry about this right now. Right now, just take a look at whatever we have studied so far in 5 to 6 hours. This has been mentioned in the code in only 5 lines of code. So it really does not do justice to the amount of depth which is actually in all of this. There is a question of what is the logits, right? Logits, it's this final output, this step, this output head. So this matrix which we get, which is of the size of 4 multiplied by 50257, that's called as the logits matrix. And we saw this matrix also here. This matrix, right, which is the size of the input sequence, number of columns equal to vocabulary size. That's called the logits matrix. Actually, you apply softmax to it. So ideally, this matrix should be called the logits matrix once you have applied softmax. Okay. Does anyone have any doubts or any questions in this part so far? So if you go through this entire code block once, let us recap what all we have seen, okay? First, what we did is we started with my data set. The data set which we are using is this Hugging Face Tiny Stories data set. And then what we did is once we have downloaded the data set, the next step is we did two things. And those were very important two things which we covered in the first lecture. The two things which we did once the data set was downloaded is we tokenized the data set and we stored all the token IDs in one big file. Actually, two big files, train.bin and validation.bin. So imagine all the sentences being dumped into one place. We tokenize it using the byte pair encoding, convert it into token IDs and put all the token IDs in two bags, a train.bin bag and a validation.bin bag, right? Then what we do after this step is that we create a function. We have written this function called get batch, and many of you were confused at this point that why did we write this function called get batch? The reason we have written this function is that whenever we get the loss, we are going to call this function to create the input output pairs for us. This function creates the input output pairs for us. What is the size of the input and output pairs? The number of rows in the input matrix are determined by the batch size, and the number of columns are determined by the context size. Right? Yeah, so this block size here is the context size, and this batch size here is the size of our batch which we want. So get batch essentially converts the data into input and output pairs. Right? And then what we do is that you might be thinking, okay, we get the input output pairs. When is it actually passed to the transformer architecture or the whole architecture? The way it's passed is that you get the input output pairs, right? And then this is that place where the input is passed to the data. And the ground truth is also input is passed to the model. So the input is passed to the model. The ground truth is also passed to the model here. And then what happens is what we covered in the last lecture. Once the input X, so now think of this input, this is the X. When it's passed through the model, it's passed through this question mark, which is all of these steps. It goes through the input, it goes through the processor, it goes through the output. And the result is a prediction of the next 4 tokens. Right? Once we have the prediction, we have to get the loss somehow, right? And the loss, the way we get the loss is that, so see here, you have token embedding, position embedding, you add those two. Someone has asked a question that where do multiple blocks come into the picture, right? It's over here. So you go through the first block, it's a for loop basically. So you go through the first transformer block, then the output of the first transformer block goes to the second transformer block, etc. When you come out of all of those transformer blocks, you have the output head. And then here is where you get the loss. Right? And so what you return is essentially logits comma loss. So you get the loss function over here. So this one line which is mentioned over here, this cross entropy, is what we covered in a large portion of the initial part of today's lecture, which is this portion. So usually if you just take a look at the code, it's very difficult to understand anything because every single line here, for example, these 5 lines of code, these 5 lines are actually this entire architecture, right? So just going through the code does not explain anything really. You have to accompany it with a theoretical understanding. So then you might be thinking that where is my training loop, right? We are going to come to that. So once we define the loss function, here is where the training configuration is defined. The block, we saw some hyperparameters over here, but not all of them. The remaining hyperparameters are defined here. The batch size is defined here. The block size or the context window size is defined over here. Gradient accumulation steps are also defined. And these are the parameters for the learning rate. Remember, we are using a ramp for the learning rate. These are the parameters here. So that's the training configuration. And here is where we define the optimizer, which is the ADAM optimizer, which we are going to use. And we are going to use this warm up and the decay in my learning rate, which we already saw that. The main pre-training loop of the SLM is this. And what happens in this pre-training loop is that, so you start going through the loop. First, what it will do is that it will call the estimate loss function. Here is where the entire forward pass is happening. Because as soon as this estimate loss function is called, what will happen is that we'll go to this estimate loss. We'll get an input output batch. We will pass that through the entire module and we'll get the loss. The loss which you get over here, uh, then you just print out what's the loss which you have obtained after one batch is finished, etc. And you define evaluation iterations over here. Basically, what it means is that after every 500 iterations, you print out the loss. That's why here you see after every 500 iterations, we are printing out the loss. That's what this eval iters is doing over here. That's it actually. The training loop is very simple if you understand which are the functions which are being called. And this part is for the gradient accumulation steps. Because remember, we process one loss which can fit in the whatever gradient accumulation steps which we have. This part is done to make sure that our GPU memory is not overloaded. Where is the negative log probability? Negative log probability is actually mentioned here itself. So cross entropy, right? This f dot cross entropy, this is a Python function which by default implements the negative. So if you learn about, if you look at this function and if you see what this function actually does, you'll see that it implements the negative log likelihood basically. So what we are seeing here is after every 500 batches are finished, we are printing the training loss and we are printing the validation loss. There is a question about gradient accumulation, right? Yeah, let me explain this part once more actually. So the thing is, if you see, yeah, one batch itself, if you consider our batch size right now, in our code, our batch size is equal to 128, right? This means I will have 128 input. I have to process 128 input output pairs. And then I have to get all their gradients and accumulate them. So without gradient accumulation, what is done is that I do my first batch, I do my second batch, I store its gradient, I store its gradient, I store all of these gradients of the 128 batches in my memory. And then finally, I take the average of all of these. That's what you do if you don't have gradient accumulation. But in gradient accumulation, what you actually do is that you just do this micro batch. So you have a micro batch of only 32 examples. You find the loss on these 32 examples, right? And then you get the backward method basically. Then you get the gradient. And now nothing is stored in the memory. Only this gradient value is stored in the memory. Then you go to the second batch. Then you get the second gradient that's added to what we store in the memory. So at one time in the memory, only 32 examples are processed. Whereas here, if you don't have the gradient accumulation, 128 examples are processed at a time in memory. That's the main problem if you don't do gradient accumulation. And so now when you run this, how many of you are able to see this training and validation plots? Actually, can you post your training and validation plot on the chat? There is a question by Krishna. Parameters remain in memory. Yes, that's correct. Here we are talking about the gradient values of the parameters. Yeah, I can see that the plot, the train and loss values for many of you are overlapping. That's very good. This is a sign of the fact that we are generalizing well and we are not overfitting. If we are overfitting, it would usually mean that the validation loss is much higher than the training loss. Now what you can do is that once our pre-training is done, now we move to the last step of the SLM pipeline. And the last step of the SLM pipeline is essentially inference. So what is done in inference is something very simple. Now you have all the parameters which are fixed. During the inference stage, the parameters of the model are fixed. So what happens is that you just you take whatever input sequence you want. You take whatever input sequence you want. It goes through the entire model architecture and you produce the next token. That next token is then appended to the input sequence. Then this appended input sequence goes through my model and then I get my next token. Then this next token is further appended. So then the next token generation actually continues this way. And what I've shown in the circle is actually just this. What I've shown in the circle is this entire architecture. This is that circle. But now all the parameters are fixed. So remember, we are not doing any back propagation or anything during inference. Everything is just happening in the forward pass. So here is where, so you get the, so this is the real test of whether our model is actually generating coherent stories or not. Remember, we have taught the model nothing about English language. We have taught the model nothing about subject, verb, object. We have just dumped data and we have collected all the token IDs in a training bag and a validation bag. That's it. And we are just training on next token prediction task. So let us do this inference now. So we have defined a generate function over here, which actually generates new tokens. So you can run this part. So first we can save the model which has the best parameters and then we can run this. So now here is the story which I have generated. Once upon a time there was a pumpkin. Once upon a time there was a pumpkin. There were many beautiful fountain and burning. The person was embarrassed and helped the pumpkin and they were all harmful. So you can already see this is quite cool, right? Remember, we have not taught the model anything about grammar, but all the sentences seem grammatically correct. Tom's dad made some cereal on the floor. Delicious cake was left, etc. So now if you run the second sentence, a little girl went to the woods. A little girl went to the woods. She was looking at the animals and their kind dance. See all of these sentences. How is the model generating? This may not be present in the training data at all. And we had less than 100 million parameters in our entire model architecture. And we have reached a point where sentences or stories which are being generated are in cohesive grammar. Can all of you put your stories over here? What are the stories which you are seeing? Yeah, so this is the first time if I really encourage all of you to run this step because it feels very empowered. It feels like we have built a language model entirely from scratch, which had no clue of the English language before, but now it has somehow learnt about the structure and the meaning of the language in less than 100 million parameters. And that's very nice to see on our own. So I can see some stories which have already been uploaded, right? This is something which has been generated by AI. No human has generated these stories. Maybe they did not exist in the training data set at all. So all of you who have run this right now, I can see that uh, Fazil, Sita, Monideepa, Avoga, Priyanka, Dishant, all of you have run these, right? That's very good. In fact, it's amazing that all of you have seen the inference stories which are being generated on your screen. Here is a small language model which works and it works very well. So this kind of proves when this paper was released, we have now replicated this paper actually. Now it's just about increasing the number of epochs to get better and better stories. So I have actually tried for 60,000 epochs as well. If you run it for 60,000 epochs, you actually get much better stories and the loss decreases even further. So this paper, which became famous at that time, it showed that you don't need models of trillion parameters to generate cohesive text as long as you train it on a specific data set. So the results which they have got, we have kind of replicated it, right? And they just evaluated these results on several benchmarks after this point. Actually, our team, what we did is we went one step further and we also have developed something called regional tiny stories, which implements tiny stories on regional languages. So we took their framework and we implemented tiny stories on three languages, Hindi, Marathi, and Bangla. And we got incredible results here also. I'll share this paper with all of you. After this, after you have actually built this SLM from scratch, you can really add any more layers after this point. You can add the mixture of expert layer. You can add the neural network. You can modify the neural network architecture the way you want it to. But this code which I've shared right now, if you want to augment it to multiple data sets, I'll just tell you how to do that. Meanwhile, let me see some questions in the chat. Can we know the exact number? We can know the exact number of parameters. There is a function actually, model dot parameters or something. If you search about this on ChatGPT or Google, you'll get one very specific function. Once you have loaded the model, it's just model dot parameter count or something, I think. Uh, GPT-2 is now a small language model. Yeah, exactly, it is. Now let me explain to all of you the procedure of how to adapt this code to other specific data sets. So if you see, this code is completely generalizable. You can go back and play around with various hyperparameters such as vocabulary size, context size, number of transformer blocks, attention heads, embedding dimension, dropout rate. The thing which is really very important is data set. And the reason why this code worked so well for us is right now because we had a data set which is specific to what 3 to 4 year old kids can understand. So if you want to build an SLM for any domain, you have to have a data set which first teaches the model about the English language, and then you have to have domain specific article about your particular domain. So that is going to be very important. Uh, what we are going to do actually, we'll have one more session tomorrow. In tomorrow's session, what we are going to do is that, so regional tiny storage is completely open source. You can get the GitHub code for this and just try mimicking the code for any language which you want. In tomorrow's session, what we are going to do is that we are going to do two things. First, the first thing what we are going to do in tomorrow's session is we are going to replicate GPT-2 entirely from scratch. So currently what we have done is that we have kind of mimicked GPT-2 architecture, but we have not replicated their results, right? So if you see GPT-2 paper, I think this was the main GPT-2 paper, and we are kind of going to try to replicate the results as much as possible. And the way we are going to test this is that we are going to try to replicate. Let me show you the kind of results. Or what we are going to do is that we are going to take this data set, which is a lot more larger than what we currently had. Currently, we only had tiny storage data set, right? Tomorrow, we are going to work with this fine web data set, which is a representation of all the knowledge in the world. And we are going to use 10 billion training tokens. And we are going to load this data set first. Second thing which we are going to do is we are going to actually chain 8 GPUs together. Because to actually replicate GPT-2 on this huge data set, this data set which we are going to look at tomorrow, this fine web is huge. It's about 100 times larger than the data set which we saw right now. So to actually do this, we are going to chain 8 H100 GPUs together. And this would need around, if you want to budget it for 1 hour, this would take around $20 to $25 of budget. And any one of you who is planning to replicate this with me in tomorrow's lecture, all you have to do right now is you have to go to RunPod. You have to go to RunPod and you have to add this much budget on your account. So this will be a production scale demonstration of how we can chain 8 H100 GPUs together on this fine web EDU dataset to replicate GPT-2 results fully from scratch. We won't be able to run all iterations tomorrow in the class time frame, but I'll try to do as much as possible live. Then what we are going to do tomorrow is that after this is done, I'm also going to show you how to create an SLM for biomedical domain. Basically, there is this paper called BioGPT. And that's a small language model specifically developed for biomedical data. So I actually tried to replicate this from scratch and I've got good results on this. So if all of you are thinking that this tiny stories data set is nice, but how can I get it for my specific domain? I'll show you how to do it for a biomedical domain, and then you can do it for any domain which you want, whether you want to do it in mental health domain or civil domain, construction domain, etc. You can follow the template which I'll share with you for the biomedical domain. Actually, if you see the BioGPT paper, This is the paper which I tried to replicate. It's not easy, but I tried to put it in the Google Colab. So this we are going to see tomorrow, okay? So tomorrow is going to be two things, the FineWay BDU and the BioGPT. So someone is asking, didn't we replicate GPT-2 in build in LLM from scratch? No, we did not. In LLM from scratch, if you are referring to the build LLM from scratch YouTube series, there I did not replicate GPT-2. We borrowed the pre-trained weights from GPT-2, if you remember. We did not replicate it from scratch. Before coming to tomorrow's lecture, actually it would be good if all of you can do two things. First is read through the GPT-2 paper. These results we are not going to exactly able to replicate, but at least we are going to replicate Nano GPT fully. Whatever was obtained in Nano GPT, we are going to replicate these results. So I think it's there, Nano GPT. Yeah, these are the figures which we are going to replicate. This figure. We are going to see how what GPT obtained and going to have our own figures. So it will be good if you read the GPT-2 paper. Actually, I'll share it in the chat. And one more thing uh, is that BioGPT, right? Yeah, so BioGPT has made their repository also public, I think. They have made it public, so you can take a look at it. And you can, it's very difficult to understand anything from their repository. So my goal is to try to break it down to concepts which we have already learned. They have made it very complex actually. I have still not fully replicated it, but I am on a good track, I think. This is that paper, which also you can check before tomorrow's lecture. And the data which we are going to download is FineWay BDU. I'll show that in tomorrow's lecture also, what is the data which we are going to download. The model produces one token as the output each time. And tomorrow, I actually did not intend for tomorrow to be a part of the bootcamp, but I expected the lectures to be finished in 3 sessions, but they have not yet finished. So tomorrow we'll actually do these two things. But you will not be able to run tomorrow's sessions unless the BioGPT will do it on A100 on Google Colab. But to replicate GPT-2, we will need at least this much amount of budget on the run pod. If you don't have it, it's fine. You can just come and watch. But Google Colab Pro subscription, it will be good for you to have so that you can follow along for this BioGPT part. There are many questions on reinforcement learning, distillation, etc. I won't cover this like this in this class because those are not in the scope of our bootcamp. Okay, so far we have 3 sessions. We have had 3 sessions and they have almost been 5.5 to 6 hours. Tomorrow, I think I'll need one more hour. So our entire learning can be captured. People who have registered for the pro plan, you also have access to these notes. So I'm deliberately not removing the notes which I've made in class. So they are in the section called in class notes. And I'm also preparing a PDF material based on these notes, which I'll share in Discord. Thanks everyone. This won't be uploaded on our YouTube channel right now. We are maybe upload it next month or the month after that. Thanks everyone. I look forward to seeing you in the next session. I hope all of you ran this right now to get the feel of what it feels like to make our own LLM and see the responses. So here we did everything from scratch. There was no library which we used. Those who have not run this, if you're on T4, it might take 8 hours, I think. But you can try to run it and then report back the results tomorrow. So tomorrow lecture will be at the same time and it will be the last lecture of this bootcamp. Thanks everyone. I look forward to seeing you in tomorrow's lecture. Bye.